In 9.8, we're going to seemingly change gears from what we were focusing on from 9.2 to 9.7, and that was testing infinite series to see if they're converging or diverging. But there's going to be a connection that's going to be made to all of what we did from 9.2 to 9.7 to a little bit later in Chapter 9. So really look at Chapter 9 as two halves in a manner of speaking. The 9.2 to 9.7 stuff that we just finished going over, and then the 9.8 to 9.10 stuff. And again, these two things are going to be tied together, but it's not going to feel that way maybe here in this first section of with 9.8. Here in 9.8, we're going to look at approximating functions using a polynomial, and that polynomial is called a Taylor polynomial. We've actually kind of done this prior in this class, back when we did tangent line approximations. So we'll kind of review some of that and lead into what these Taylor polynomials are. Okay, so again, remember, eventually all that stuff from 9.2 to 9.7 that we worked so hard on will eventually play a part here in the later parts of Chapter 9. But for now, let's think about evaluating complicated functions like sine of 4 without a calculator. And that's not 4 degrees, by the way, that's 4 radians. So what would the sine of 4 be without a calculator? Well, when you're faced with a hard problem, what do? We don't do it. We do an easier problem instead and see if we can kind of work our way up to the answer that we're looking for. So a good strategy that we've seen before in this class is if we can't evaluate a complicated function, we can certainly evaluate a polynomial that would approximate that function. And again, we did that with our tangent line approximations. So of course, just as a quick example of an illustration of what I mean, let's propose, and it's not true, but let's propose that this function right here would give you an approximation for sine. Well, if that function would give you an approximation of sine, then of course we would rather do this function where we plug in 4 instead of trying to figure out what sine of 4 is. So that being the case, of course, we could just plug in 4, and I'm not going to go over the math, but that's again just to serve as an illustration of why we're doing this polynomial approximation. Because we can do this without a calculator. Sine of 4 is impossible without a calculator, but of course we could just plug in 4 into this polynomial, and maybe this would be our approximation of that. But again, that's really not what it is in this particular case. So let's recall back from 3.9 when we looked at our only type of approximation we did, and that was using a tangent line. Tangent lines usually do a pretty good job of approximating curves. So tangent lines are actually polynomial approximations of curves. And here's a quick little picture. Let's pretend we have this function in purple that we don't know, and let's pretend maybe that's our sine function. What we could do is, instead of finding sine of 4, like we can't do, what if we wrote a tangent line equation at that point? And then found that equation and pretend maybe it was this equation. Of course, it's not a linear function, but let's pretend that was the function. Then of course, we would rather plug in 4 into a polynomial than into that complicated trig function. So that being the case, of course, we started off with our good old point slope formula, and I'm going to use this information here to write out the version of this that we need. So of course the point that we're looking at here is c comma f of c. So our tangent line, for our tangent line, we need a point and a slope. We already have our point, it's c comma f of c. So of course we need our slope, and to find the slope we would take the derivative, which would be f prime, and well, f prime of x, and then we need the tangent line at that point c, so it would be f prime of c. So we can take our point here of c comma f of c, and we can take our slope here and plug it into our point slope form. Of course, that looks way more complicated than we ever really saw it back in 3.9, because we actually had numbers here, here, and here. But ultimately, I'm trying to generalize this so you can see where we're trying to go in this new chapter 9 now. I'm going to just kind of move over that f of c by adding it to the other side, and then we would end up with this. This would be the equation that we could use to approximate this function f of x that we don't know. And again, of course, there were numbers in all of those spots. So don't look at this as something new. Please just look at this as what we did back in chapter 3, which was nice and simple. And I'm putting brackets around that because remember, all of this needs to be multiplied before you add that f of c value. Okay, so where do we want to go with this problem? Well, we want to try to improve this tangent line approximation because, of course, as we get further and further away from that point of tangency, the gap between our tangent line and our function kind of gets worse and worse. So can we improve the tangent line approximation? Well, yes, let's kind of talk about how we can do that. Can you approximate sine x using a polynomial? Well, of course, if we wanted to use just the most simplest polynomial of them all, we could use that horizontal line. But you could see right away, if that line was to be used as an approximation, then we'd have these big gaps right here between where the function really is and where our approximation is. So of course, that wouldn't be very good. But what would be a very good thing to use? Instead of our tangent line approximation, which you can see right here, a better approximation might be some sort of curve, some sort of parabola, upside down parabola. So that's kind of the idea. The requirements for putting a parabola here instead of a tangent line would kind of be like a tangent line, but we need some more information. We need some stuff to correspond. We need three things to actually correspond. For a parabola to pass through the same point on this function sine of x, our zeroth derivatives would have to agree. Now, that's just really a fancy way of saying is that the point on our parabola and the point on our function have to be the same. So hopefully that's not too complicated to understand, but that's what we're saying here. The zeroth derivative, in other words, the no derivative, in other words, the point, for both of these things have to agree. The next thing that has to agree is that, of course, they have to have the same slope at this point right here. And again, we're trying to look at this point right here, pi over 2. So not only do we want the point on our purple and red function to match up, we would also want the slope to match up because they would have to have that same shape. The next thing we would want, of course, to have match up is the second derivative. We would want the points to match up so that those are in line, and we would want the slopes to match up. But even more so, we of course would want the concavity to match up, which would be the second derivative. We of course don't want a concave up parabola, we want a concave down parabola, so we would want the second derivatives to match up as well. So the bottom line is yes, we can find a polynomial. If we can find a polynomial whose derivatives agree with sine of x, then we can approximate this function. And it's just an extension of what we saw back in chapter 3. I promise you, it's just one extra little bit of information we have to use, and it's essentially what we were doing back in chapter 3, except we're taking it one step further and using curves instead of tangent lines to approximate functions that are a little too complicated. Okay, so what is this polynomial called that we're going to use? Well, in 3.9 we of course used a tangent line, so it's called a tangent line approximation. The thing we're going to use here in this chapter, and it's going to be a curve, not a tangent line, is going to be defined by a Taylor polynomial. So what is a Taylor polynomial? Well, a Taylor polynomial is going to be the thing that we're going to use to evaluate complicated functions at certain points. The example we can use is sine of 4. We can use a Taylor polynomial to approximate sine of x and then plug in 4 instead to that polynomial instead of the sine function. Okay, so let's try not to get lost in this new notation for this Taylor polynomial, but here we go. We define a kth Taylor polynomial that's centered about x equals c as this right here. Very important, just like a lot of the things I box in red, which means you're going to have to memorize it. And I know it looks complicated. It's definitely one of those things where if you don't break down what's going on here, it's going to seem more complicated than it actually is. So what is this? Well, this is just a polynomial that we're going to make. This is what I'm going to call a polynomial machine. In other words, if we start plugging in n equals 0, n equals 1, n equals 2, n equals 3, and so on, it's going to produce a polynomial, some sort of equation. And how big of an equation is that going to be? Well, that's going to be determined by where we stop. When we say we have a kth Taylor polynomial, we're talking about however many terms are going to be in this polynomial. So of course, if this k was 2, we would have this expanded out to the second degree. If this was a 3, then we'd have a third power. If this was a 4, then we'd have a fourth power. So that's all that means. What is this notation right here? Well, the p, I guess, just really stands for polynomial, I suppose. And of course, this n is the degree of that polynomial. So whatever that happens to be. Again, if it's like a second, or if it's a quadratic equation, then that would be a 2 there. So then what is this Taylor polynomial telling us here? In the top of this fraction here, and you're going to have to recall this way back from chapter 2, when we have a parentheses around a power, it's not a power. It actually indicates the order of a derivative. So if there was a 2 here, that would be a second derivative. If there was a 4 there, that would be a fourth derivative. So what we're doing is we're taking some derivative value and dividing it times n factorial. And then we're multiplying by x minus some value c to the nth power. So other than spending the time of going over where this formula comes from and why all this exists, a better use of time here will be practicing using it. So again, this will just kind of have to be something we memorize and use from here on out. So let's practice expanding this Taylor polynomial. And again, this Taylor polynomial is going to be of degree k. So let's just practice expanding this thing. And again, I'm going to call this a polynomial machine. In other words, if you start plugging in values of n in here, it's going to produce a polynomial. So let's go ahead and practice doing that. We're starting at n equals 0, so the first thing we need to do is plug in 0 wherever we see an n. So we're going to have the 0th derivative at c, that's just some point that will be given to us, over 0 factorial x minus c to the 0 power. Keep in mind, there needs to be a plus here because we're summing. We're doing a summation here, so of course there needs to be a plus there. The next term will look exactly the same, but everywhere that there was a 0, we're going to now put a 1. And again, that's where those n's are. So it'll be the first derivative of c over 1 factorial x minus c to the first power. Again, we need to add to that, and I'm going to produce another term. Again, this is like a little machine that's giving us each of the terms of this polynomial. So now we're going to have the second derivative of c over 2 factorial x minus c squared plus dot dot dot. Of course, we can stop wherever we want to stop, but we're going to stop at k. So of course, that final term, whatever it happens to be in the problems that we're looking at, will be the kth derivative of c over k factorial x minus c to the k power. So definitely practice expanding this out. It's going to be something we're going to use for the rest of this chapter now. So some things to point out because we can clean this up. 0 factorial is equal to 1. I won't go over the details of why that's true, but if you remember back from earlier in this chapter, we defined 0 factorial as 1. So of course this entire thing right here, this entire first term just becomes a 1. X minus c to the 0 power is just 1. So when we multiply everything here, all of that becomes 1. And of course, we're just left with the 0th derivative at c. And again, remember, a 0 derivative is just a way of saying a point. If we clean up this next term, of course, 1 factorial is 1, and we don't need the power of 1. 2 factorial is 2. And then we can just end there with that general term, or the kth term, where we can't really simplify it. So there's something we need to realize. We've actually been using a Taylor polynomial since we did 3.9, where we saw a tangent line approximation. And it's very important that you make that connection. We actually have our tangent line approximation right in the first two terms. If you take a look back at the previous slide when we wrote out our tangent line approximation back from chapter 3, that actually matches up here. The 0th derivative, remember, is another way of just saying, what is your y value, f of c? Again, this notation with the parentheses and the 1 is a first derivative, or we can write that as f prime. And then, of course, we have x minus c. And again, remember, this c value is the point in question that we're trying to approximate. So don't be thrown off by that c. Okay, so I know that's a lot. Like you've heard me say many times in this chapter, please rewatch some of these parts of these slides if some of this isn't quite sinking in the first time. But that's the idea. We're going to use these polynomials, depending on what size they're going to be. It can be 2, 3, 4, 5, or whatever, to approximate complicated functions. There's one other thing we got to go over real quick here, and that is what is called a Maclaurin polynomial. Taylor was the mathematician who came up with this, and then another mathematician named Maclaurin came up with a little alteration to the Taylor polynomial, and that is when a Taylor polynomial when c is equal to 0. And really all that changes is we just plug in 0 for c, since that's the point that we're going to be centered about. And again, that's just the point in question, so to speak. So if we rewrite our Taylor polynomial with a value of 0 for c, then we just end up with what you see right here. It's just the same thing, but using a different value for c. And again, the value of c would just be 0. So it just turns out to be the nth derivative at 0 over n factorial times x to the n power, again because c is equal to 0. So we'll practice using these two things. Each problem is always different. Sometimes it's Taylor, sometimes it's Maclaurin, but ultimately if you know the Taylor polynomial, then really you know the Maclaurin polynomial as well. Okay, let's see if we can put these Taylor polynomials to some good use. Of course, or I hope you realize, a natural log is very hard to do without a calculator. Natural log of 2, we don't really know how to do. I think we can all agree it's definitely a complicated function to do without a calculator. So what we want to do is write a fourth Taylor polynomial for the natural log function, and that's going to be centered at 1. So let's go ahead and do that. The very first thing we need to start off with is we need to find a bunch of derivatives. If you think about the expansion of our Taylor polynomial from the last slide, every one of those terms needed a certain derivative. We needed the 0th derivative, we needed the first derivative, we needed the second derivative, and since here we're going to a 4th degree Taylor polynomial, we of course are going to need a 4th derivative so we can find some values. So let's go ahead and list these off. I'm going to try to break down this Taylor polynomial into some steps to kind of make it a little more manageable. So we need to find a bunch of derivatives up to the 4th derivative. So of course the 0th derivative is just the function itself. We haven't taken a derivative. So that's just natural log of x. The first derivative is 1 over x. The second derivative would be negative 1 over x squared. I'm going to skip over the steps of explaining this, so hopefully you're okay finding these basic derivatives here. The third derivative would be 2 over x cubed, and the fourth derivative would be negative 6 over x to the 4th. So, assuming you're okay with your derivative skills here, that should be nice and simple. So what do we want to do? We want to find this Taylor polynomial centered at 1, which means we need to evaluate all of these derivatives at 1. So I'm going to put this bar here. It's really to separate step 1 and step 2 here, but it's also to remind you that this bar is telling you to plug in x equals 1 into all of these derivatives here. So when we do that, we'll end up with 0, 1, negative 1, 2, and negative 6. So why did we go through that? Why did we need to find these derivatives and then plug in 1? Well, again, if you think about a Taylor polynomial, if we expand this out to the 4th degree, we're going to need all of these values right here to plug in. And I didn't really mention it as we were trying to do this in the last slide, but really this is the only thing you need to make these problems work out. As long as you have those values, these problems are very, very easy and straightforward. Now sometimes it can be a little hard to maybe get those values, but that's the idea. So I would start with just writing out the Taylor polynomial machine, this machine that generates a Taylor polynomial. And we want to generate this machine up to a 4th degree. So the very first term, if you remember from the last slide, will just be the 0th derivative at c. The next term will be the first derivative at c times x minus c. And don't write this in, but remember this is really over 1 factorial to the first power. But we don't write that in just because that makes it more complicated. The next term would be the second derivative at c over 2 factorial times x minus c squared. The third term would be the third derivative at c over 3 factorial times x minus c cubed. And since we want a fourth degree Taylor polynomial, we'll stop right there at 4. It's going to be the fourth derivative at c over 4 factorial times x minus c to the fourth. So that's the thing that you guys have to get practice doing. That's the thing that's going to really determine how easy or hard you make these problems. Okay, so we want to generate this Taylor polynomial centered at c equals 1. So we just need to take 1 and plug it in for all these c values. There's a c here, 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 and you can see all those c values in our Taylor polynomial. So if we plug in 1 there, we end up with this. And now it's just a matter of plugging in our numbers. We know the 0th derivative at 1 is 0. We know the first derivative at 1 is 1. And we're just going to keep plugging those values in for each of these derivatives. Again, that's really the key to these Taylor polynomials. Once you kind of break everything down, you really just need some derivative values, which we've known how to do really since chapter 2. The only other thing I'll mention is 2 factorial. I'm going to write expanded or multiplied out, so 2 times 1 would be 2. 3 factorial would be 3 times 2 times 1, or 6. 4 factorial would be 4 times 3 times 2 times 1, or 24. When we plug all of our derivative values in, we'll end up with this. And of course, we can simplify that a little bit and clean it up. The 0 we don't need. 1 times x minus 1 is just x minus 1. Minus 1/2 x minus 1 squared. The 2 over 6 becomes 1/3. The negative 6 over 24 becomes negative 1/4. And then we'll end it with x minus 1 all to the 4th power. And again, be careful with the notation. This p is really just saying it's a polynomial, and this little subscript of 4 is telling us it's a 4th degree, which of course we can see just by looking at it over here, but that's the notation we use. Our 4th degree Taylor polynomial is given by what we have here boxed in red. So what does that even mean? What did we even do? How can we even use this? Well, just realize how we can view this Taylor polynomial. And I'm going to graph each piece of it. So for this first part, pretend all of this didn't exist. Pretend we just did our tangent line approximation, which was this piece, which is a linear function. This graph in black down here is our ln of x graph, which wasn't labeled, but that's our ln x graph right there. And you'll notice this graph that's linear doesn't do a very good job of approximating ln x. It's not very good. There's a giant gap right here, and if we wanted to find ln of 3, this would be a pretty bad approximation. So let's pretend we wanted to graph just the quadratic piece of it, which would be the first 2 pieces. So we'll pretend that these 2 don't exist, and let's graph that and see what it would look like. P2, the 2nd degree polynomial. Well, again, this is our natural log graph, and you can see our approximation has gotten a little bit better. It's now curved and not just a straight line, but it could still be a little bit better. So what if we graphed the cubic piece of this polynomial? In other words, what if we ignored this last term and just graphed that polynomial? Well, now you can see our approximation is getting a little bit better now. It's still our natural log function here, but now this curve in gray is kind of I guess mimicking our natural log function a little bit better. What if we graphed the entire thing, the whole 4th degree Taylor polynomial? What would that look like? Well, now you can see things are getting even better. Over here on the right side of this polynomial, it's not so good for the natural log. But over here, it looks pretty close to our natural log function. Of course, if we went out to a 5th degree or a 6th degree or a 7th degree, this approximation would just get better and better and better and better. But for this problem, all we needed was a 4th degree Taylor polynomial. And these pictures down here are just to kind of give you an appreciation of how each of these powers, so to speak, makes the approximation get better and better and better. As a usual follow-up question, what if we wanted to approximate the natural log of x? The natural log of 1.2. Well, remember, without a calculator, that's basically impossible. We don't know how to find the natural log of 1.2. But we could, of course, instead plug 1.2 into our Taylor polynomial here and see what that's equal to. That would be an approximation and not an exact answer. So it turns out if you were to plug in 1.2 into our fourth degree Taylor polynomial, which would be p of 1.2, we would end up with an approximation of 0.182. Okay, so hopefully that first example, while it was lengthy because of the steps I kind of broke down, hopefully now you're getting the hang of what we're even trying to do here. We're trying to write out a polynomial that will approximate a function that's kind of a little too complicated for us to do. So here we want to write a fourth degree, not Taylor polynomial, but Maclaurin polynomial. And it doesn't have to tell us this because we're going to have to know this, but of course that means c is equal to 0. That's what a Maclaurin polynomial is. So just like the last problem, since we want a fourth degree polynomial here, we need 4 derivatives. Luckily here, this is very simple because of the function we're given. The 0th derivative, again, is just our original function, so we don't do anything to it. And then luckily, every derivative is itself. The first derivative is e to the x, the second derivative is the same, the third derivative is the same, and the fourth derivative is also the same. So luckily, that was nice and simple in this problem to take those derivatives. Again, we're dealing with a Maclaurin polynomial here, so we need to know that that's centered about x equals 0. Or in other words, we need to plug in 0 into all of these derivatives. Luckily, they're all the same derivative, so e to the 0 power would always be 1. Okay, so now that we have our derivative values that we need, and hopefully again you're realizing after that first example that's really all we need, we can go ahead and write out our fourth degree Maclaurin polynomial. So I'm going to start off with the machine that generates a fourth degree Maclaurin polynomial, and then we can expand it up to that term. So let's go ahead and write out each term. Again, the first term will be the 0th derivative, and we're just going to start plugging in our c value of 0 here. So it'll be the 0th derivative at 0. We're going to have the next term, which would be the first derivative at 0 times x. But again, technically this was x minus c to the first power. But again, remember c is equal to 0. The next term will be the second derivative at 0 over 2 factorial. And again, remember this term was technically x minus c squared for a Taylor polynomial. But this is Maclaurin, so c is equal to 0. For our third degree term, it'll be the third derivative at 0 over 3 factorial times x cubed. Again, that was really x minus c cubed, but c is 0. And then for our last term, it'll be the fourth derivative at 0 over 4 factorial times x to the fourth. And again, the reason we know that there are these zeros here, here, and here is because from our Maclaurin polynomial, we know c is 0, or this polynomial is centered at 0. Okay, so just like a Taylor polynomial, a Maclaurin polynomial just needs you to get all of these derivative values that I'm circling and plug them in. Luckily, we already did all that work. It doesn't really matter what order you do this in. You could, do step 3 first and then do steps 1 and 2, or you can do it like I'm doing in these examples. But ultimately, we just need those derivative values so we can plug them in now. And luckily, all of those derivatives have a value of 1. And of course, to simplify this, it's nice and simple. It's just going to be 1 plus x, and I'm going to go ahead and leave the factorial notation. Sometimes there are multiple choice answers on the AP test where they'll multiply it out, and sometimes they'll just leave it as the factorial. It actually doesn't really matter if you multiply that out or not. So of course you could write instead of 2 factorial 2, you could of course write instead of 3 factorial 6, and instead of 4 factorial you could write 24. Other than that, that's it. That's our fourth degree Maclaurin polynomial for the function e to the x. And actually there's a little typo here, I guess. It really shouldn't be p sub n right here. It should really be a 4 for the fourth degree Taylor polynomial, or Maclaurin polynomial. Okay, so let's see what we can do with this. If I were to take e to the x and graph it, and if I were to take this this Maclaurin polynomial and graph it, how good of a graph would we get for this approximation? Well, if we take that and graph it, you'll notice how good it does of a job. All of this area right here of this graph is basically right on top of the graph of e to the x. Of course, it does a pretty bad job over here of approximating e to the x, but luckily, if we were trying to approximate anything over here, it looks like it would do a pretty good job of approximating that value. If we wanted to find e to the -4 power, I guess this wouldn't work out so good. This polynomial wouldn't do such a good job. But if we wanted to find any value of x, certainly from 0 to the right, I think we'd be looking at a pretty good approximation. So just to prove that, let's go ahead and find the value of e to the 0.1 power. And I'm going to show this like you'd see it in your TI-89. I'm going to do it both ways. Here in the top, or in this first line, what I'm doing is taking the 0.1 and plugging it, if you look at the calculator notation, I'm plugging it into your Maclaurin polynomial that we found. And what it turns out is that we get a value of 1.10517. So that's our approximation. So how good of a job does this this Maclaurin polynomial do? Well, if we take the calculator and let it do e to the 0.1 exactly, it turns out to be the same exact value to those 5 decimal places. And that's not a surprise based on this picture that we have to the left. E to the 0.1 power should be a pretty good approximation because these two graphs are basically right on top of each other. So again, hopefully with this second example, now just being a Maclaurin polynomial, you can kind of see what these polynomials are good for. We're using them to approximate functions that we can't do without a calculator, and they do a much better job of maybe than our regular tangent line approximation, which, of course, if we can do better, we would want to use these instead. Okay, so hopefully those first two examples kind of give us enough of a push in the right direction to now try an AP test free response problem using this idea of a Taylor polynomial. So here we have a table of values. We've seen these kinds of problems before where we don't know what the function here, h is. They just give us a bunch of information about h prime, h double prime, and the third and the fourth derivative at all of these values from x equals 1 to x equals 3. And that's really all we know about the function h. So in this first part, part A, we want to write a first-degree Taylor polynomial for this function h about x equals 2, which is really another way of saying when they use the word about, it's talking about that c value, so it's really c equals 2, which is really the same thing as x equals 2. It's just that critical point in a manner of speaking, that point that we're looking at for the problem. So let's do that first. Let's write our first-degree Taylor polynomial. So the funny thing about a problem like this, as opposed to the first two examples, is you actually don't have to have any calculus skills to do this problem. All we need here is just the knowledge of how to expand this Taylor polynomial, because we don't have to take any derivatives here. We're given all of these values in this table, so we just have to know how to expand this Taylor polynomial to the first degree. So the first term always will be the 0th derivative at c. The next term always will be the first derivative at c times x minus c, and that's where we can stop. We need the first degree, so that's exactly where we can stop. This next step I didn't quite animate in, but of course now we need to plug in the value of c. Here we're centered about x equals 2, or in other words, c is equal to 2. So we want to find the 0th derivative at 2, and then add to that the first derivative at 2 times x minus 2. And of course, we're going to get those values from the table above. The 0th derivative at 2, which is really just the regular function, is 80. The first derivative at 2 is 128, and when we take and plug in those values, we end up with our first degree Taylor polynomial, which is why we have that notation of p sub 1. And that's essentially it. Just as a little follow-up here, this is really our tangent line approximation because it's to the first degree, which is what we've done ever since we studied 3.8 with those tangent line approximations. Okay, I didn't mention at the top here that this was a calculator problem, but now we need to use this polynomial to approximate h of 1.9, which really just means take 1.9 and plug it into our equation, and since it's a calculator problem, we can go ahead and type that in a calculator and we'll get 67.2. Okay, the next question here that we need to address is the over or under. Is the approximation greater than or less than? Well, if you think back to 3.8, or if you just remember what we know about tangent lines, and I didn't, I guess, label it like that, but maybe it needs to be labeled as a tangent line, because it's a first degree polynomial, we need to remember that concavity tells us whether our approximation is greater than or less than. And since we're looking at the value x equals 2, our approximation would be less than because the second derivative is positive. If you look at what the second derivative is, our second derivative here is 488 over 3. So I never made note of that, but since h double prime of 2 is equal to 488, and it doesn't really even matter that it's 488 over 3, it more matters that that second derivative is positive. Since the second derivative is positive, we know our graph is concave up. And if we know our graph is concave up, then that must make our approximation less than. If you need a little reminder of what that would look like, we of course would have a concave up graph or something like that. And since we're using a tangent line, of course that tangent line would always be below our function. So that would of course make the approximation less than. So hopefully that serves as a nice little review of 3.8 and that idea of the error of how under or over the approximation is, but hopefully that was nice and clear. Okay, in part B, we just want to write a third degree Taylor polynomial now. Same thing, centered about x equals 2, and just plug in again 1.9 to see what we get. So we just need to take that Taylor polynomial and take it to 2 more steps. The next step would be the second derivative at c over 2 factorial times x minus c squared. And then the third degree would be the third derivative of c over 3 factorial times x minus c cubed. Just like from above, we're centering at about x equals 2 here. So we need to take that 2 and plug it in for all these values of c. Every place we see a c, we're going to replace it with a 2. I didn't have the space to put that in, so just kind of realize that we're finding all those values. So we need the second derivative at 2, which would be 488 over 3, and we'd also need the third derivative at 2, which would also be 488 over 3. So careful how you write this out. Of course, the first 2 terms should match from part A. Here we have the second derivative at 2, which would be 488 over 3. But then we're dividing by 2 factorial, so that 2 factorial would be in the bottom with the 3. And then when we take 488 and divide it by 3, and then divide that by 3 factorial, well, again, that 3 factorial will be in the bottom with the 3 from our fraction of 488 over 3. After that, it's just a matter of maybe cleaning this up a little bit. Of course, we can simplify, but we're not going to even bother doing that. Since the point of this problem is to take this polynomial here and use it to approximate h of 1.9, let's not chance anything, and let's not even bother cleaning that up. We're just going to leave the third degree Taylor polynomial just like this. That's what you have to be careful with on the AP test free response, is that if you take something and simplify it, that was correct, but you simplify it wrong, you kind of just messed up getting a point for that particular piece. So we're not going to simplify that at all. We're just going to leave it like that. And since we want to use that polynomial to approximate h of 1.9, we're going to take 1.9 and plug that in. Of course, we don't need to show that step or all that work. This is just going to be done in your calculator, and you'll end up with 67.988. So definitely you might want to take a moment to, again, make sure your calculator skills are where they need to be. Plug in 1.9 and make sure you can also get 67.988. Okay, so hopefully the Taylor polynomial and Maclaurin polynomial issue of writing them out and using them really isn't a big deal. It just takes some practice, and I think it's nice and simple. So if you recall in the last slide, we were able to talk about the error in terms of it being under or over in part A of that problem because it was really a tangent line approximation. A first degree Taylor polynomial is really a tangent line approximation. So of course we know concavity tells us whether it's an under or over approximation. But in general, how do we know what the approximation is, or how good or bad is the approximation concerning a Taylor polynomial of any degree? So we need to, of course, talk about the error in Taylor's approximation and how we can determine that. So the idea behind it is not hard to understand. Of course, if we wanted to find the value of f of 1, this dot right here that I'm putting in red would be the true value of f of 1. And of course, if we used our Taylor polynomial to find that, there would be a discrepancy there. That line right there that I'm drawing would be the error in our approximation. Of course, if we knew the true value and we knew the approximation and subtracted that, that would give us the error, or how far off our approximation was. So that's pretty easy to understand. That's not a big deal. Again, the true value would be this top red dot. The approximation would be this bottom red dot on the approximation polynomial, the Taylor polynomial, and of course the distance between those two, or the difference between those two, would be how far off our approximation was. But can we actually ever do that, really? Well, not really. What we're going to have to do, and it's probably the most intimidating thing to look at in this class, and it's also maybe the hardest to explain in this class, is something called the Lagrange bound, or error bound. So again, the error here is this difference. The way we can kind of address this difference is with, again, this thing called the Lagrange error bound. So I'm going to try my best to explain the details of this, but kind of look at this as a formula, and really the best way to kind of see this formula in action is just to see it in examples. So again, I know it looks very complicated, and it is pretty complicated, but let's see if we can kind of understand the pieces. So bottom line is, hopefully on this left side you're just seeing that as the error. What this Lagrange error bound is telling you is that the error is always going to be less than some value. We're actually not going to know the exact error. That's usually not anything we're going to know. But what we are going to know is that the error is less than some number, and that number is going to come from this mess over here. So just look at this entire mess as just equal to some sort of number. We'll figure out what that number is, of course, but we'll talk about the pieces of that. So I know it looks complicated, but hopefully you're seeing this just as two pieces. The left side of this thing is the error, and it's saying that the error is always less than some number, or less than or equal to, excuse me, than some number. So what is this number that we're trying to figure out? Well, there's two pieces to it. The first piece is this. What this is saying right here is we want to find the maximum derivative in the interval that we're looking at. And again, the best way I can illustrate this is by looking at an example. But in all of these problems, we'll be given some window, some interval. And what we want to do is find the maximum of the derivative in that interval. So that's the number that goes right here. How we find that, again, we'll just kind of wait till we see it in an example. The next thing we need to do, luckily it's the easier part, is to multiply by this ratio, this fraction right here. And what that fraction is the next term over. Of course, remember, with these Taylor polynomials, if you go to a degree 4, there's really nothing stopping you from going to a degree 5, or a degree 6, or a degree 7. So what this piece is just the next term after the term where you left off. And that's why there's that n plus 1 here, and that n plus 1 here. If you did a 4th degree Taylor polynomial, then this would be the 5th term. And that's, again, if you notice where we have these n's here, that's the Taylor polynomial that we used in our approximation. So n plus 1 would just be the first term that we didn't use after that. Okay, so hopefully that made a little bit of sense, but ultimately, let's see if we can make sense of this using an example here. So here we have a function f, and we know the 4th derivative of a function. We don't know what the function is, but we know that the 4th derivative is given by this. If we use a 3rd degree Taylor polynomial about x equals 0, so kind of keep in mind that's a Maclaurin polynomial, and if we use that to approximate f from 0 to 1, that would be our window, what is the Lagrange error bound for the maximum error from 0 to 1? Okay, so I know that seems rather complicated and not very clear, but let's see if we can apply this formula. Bottom line, I hope you're viewing this as kind of like a formula, so let's see if we can use this formula. So what do we need to do? Well, the first thing we need to write down is f of x. I'm going to go ahead and leave off the parentheses x part and just put the letter f. This thing is already complicated enough, so I'm going to just write f minus p of 3. Of course, we're using a third-degree Taylor polynomial because we're told that. So our error would, of course, be f minus the third-degree Taylor polynomial, or f minus p sub 3. So we know this error is going to be less than some value that we're trying to find over here in this multiple choice question. So what are we going to end up doing? Well, if you notice in this formula, actually the first thing I need to point out is our window here. We need to find the maximum from 0 to 1. Our window here is 0 to 1. This would be our A and this would be our B. So it would be from 0 to 1 of the next derivative over, or the next term over. So of course, since we used a third-degree Taylor polynomial, if you look in the formula above, that's going to be 3 plus 1 because it's supposed to be n plus 1. Okay, so now that we've kind of plugged in those numbers, now let's just go to the next piece and plug in those numbers. We're doing this about x equals 0, so this is really our c value. C is equal to 0. So we're going to have x minus 0 to the 3 plus 1. Again, it's the next term over, so we need that to be 4. Divided by n plus 1 factorial. And again, it's the next term over, so we don't want it to be 3 factorial. We want it to be 4 factorial. Okay, so that's kind of the first hurdle to get over, is setting this up. And kind of keep in mind, all of this is supposed to be one number, so I'm going to go ahead and put a bracket around all that. Okay, so let's kind of clean this up a little bit. We need to find the maximum of the fourth derivative from 0 to 1. And of course, our fraction over here just becomes x to the fourth over 4 factorial. So again, all we're doing is cleaning up this formula. The first step, we set up the formula and we just plugged in the numbers from the problem. So hopefully I didn't lose you too much there. And then the second step, we're just cleaning up this formula. And again, all of this is one number we're trying to find. Okay, so how are we going to determine this? How do we find the maximum of the fourth derivative from 0 to 1? Well, luckily, they give us the fourth derivative. So what I'm going to do is graph this function, e to the sine x from 0 to 1, and really we don't care so much about this piece. I just graphed a little bit more, but don't scribble that out, really. But either way, we just start looking at this graph from 0 to 1. And we want to find what the maximum value of the fourth derivative is from 0 to 1. And you can kind of see that. If we're looking at 0 to 1, the maximum of this derivative occurs at the right endpoint of 1. And the reason we know that is because this is an increasing function. If you have an increasing function from 0 to 1, then of course the maximum happens at 1. So again, just kind of like I said a moment ago, increasing function, so the max occurs at the right endpoint. So again, what I have in brackets right here is telling us we need to find the maximum of the fourth derivative from 0 to 1, and that happens at x equals 1. So we're going to take 1 and plug it in for x. So let's go ahead and do that. Our fourth derivative is e to the sine x, but the maximum happens at 1, so that'll be e to the sine of 1. And since our function happens to be at 1, of course we have to plug in 1 wherever we see an x. So that would mean we'd also have to plug in 1 for the x to the fourth, and then we'd still divide by 4 factorial. And of course, if you can make it up to this step without getting too lost, we just need to take that and type it into a calculator, and we'll get 0.0967, or the answer choice of B on the left. So again, I know that took a long time to explain, and I'm sure that's going to take you even longer to kind of comprehend and understand, but most certainly kind of go back and re-watch this part of this video to kind of re-hear the explanation of how we got each of these steps. Okay, so we're just going to kind of continue on practicing this Lagrange error bound, and here in this top part of this slide, I'm doing part C of the problem we did from a couple slides ago, from before we looked at the Lagrange error bound. We did part A and part B of that problem, but now we're doing part C. Hopefully you remember this table from a few slides ago, so now we're doing part C of that problem. And the reason we had to wait to see part C is because part C talks about the Lagrange error bound. So we want to use the Lagrange error bound to show that the third degree Taylor polynomial about x equals 2, so again remember that means c equals 2, approximate h of 1.9 with an error less than 3 times 10 to the negative 4. Okay, so I know again this is a very daunting task with this Lagrange error bound, but let's see if we can kind of break down what's going on here. So let's at least start off with what we know. The left side of the Lagrange error bound formula is always easy to set up. In this case, they're not using the letter f for our function, so it's going to be the letter h, and we're doing our approximation at 1.9. In that last problem, we didn't write any number there because we weren't plugging in an x value. But here we're plugging in 1.9, so this is going to be h of 1.9, which would be the exact value, and then away from that, we would have to subtract away the approximation at 1.9, and that of course gives us the error. We don't really know what that number is equal to, but what this Lagrange error bound is telling us is that error will be less than or equal to some number that we're going to get over here. And that number we want to show is less than this value. So again, hopefully that made sense as I explained that, but definitely re-listen to what I just said if you kind of need to hear that again to hopefully have that sink in. Okay, so let's go ahead and set up the Lagrange error bound for the right side of that formula. We need to find the maximum of the fourth derivative. Remember, we need to go to the next term over, so we're at a third derivative, which would mean we're looking at a fourth derivative here. We need to find the maximum from 1.9 to 2. Why from 1.9 to 2? Well, we're using 1.9 as the point we're approximating, and that's centered about 2. So that is, of course, our window. In the last example, they told us what the window was, but here we kind of need to read between the lines, so to speak, and we're trying to find the maximum of the fourth derivative from 1.9 to 2. We need to multiply now by the other piece of the term that we're leaving off, and that would be, of course, x minus c to the fourth power over 4 factorial. This is, again, our x minus c value, and again we're looking at the next term over, so since this was a third degree polynomial, this would again have to be a fourth power, just like our derivative from before in our first part of this formula. Okay, so I think really what it comes down to is, what in the world is this equal to? What is the maximum for the fourth derivative from 1.9 to 2? Because of course the other piece of this problem, we can just plug into the calculator. Well, to figure that out, we need to see, kind of like that last problem, whether the function is increasing or decreasing. If you remember that last problem, even though we don't know what this graph looks like in this particular problem, we know that the function is increasing, like you see underlined in blue here. And if it's increasing, that means the maximum value happens at the right endpoint. And that happens, of course, at 2. So here we want to find the max value at x equals 2 for the fourth derivative. And you can see from the table that's 584 over 9. Once you see that, again, all of that replaces this mess of stuff. After that, we're just going to multiply by that fraction over here. And if you do 1.9 minus 2 to the fourth over 4 factorial and multiply all that out, we'll get 0.00027. So that's our Lagrange error bound. But what this problem wanted us to do was to show that that was less than 3 times 10 to the negative 4. If you recall, 3 times 10 to the negative 4 would mean we'd have to take our decimal point after the 3 and move it 1, 2, 3, 4 spots to the left, which would then produce 3 zeros in front of the 3. So hopefully you remember the scientific notation there. And that is, of course, true. 0.00027 is definitely less than 0.00030. So there you go, another application of the Lagrange error bound. Again, I know very complicated, but with time and some maybe rewatching of these examples and practice, of course, hopefully this will become a little bit easier to understand. Okay, in this last example, it's kind of similar to the first two that we did, or I'm sorry, the first one that we did. Here we have a function f, but we don't know it. They give us a fifth derivative of this function f, and we want to use a fourth degree Taylor polynomial about x equals 0, so this would be a Maclaurin polynomial, to approximate f of 0.1. And I want to find, again, the Lagrange error bound. So the first thing we got to do, and it's the easy part, luckily, of the Lagrange error bound, is set up the left side of the formula. Here we're doing f of 0.1, and of course that's our exact value. To find the error, or to represent the error, I guess I should say, because we're not going to really find what the error is, we would have to subtract away the approximation at 0.1. And since we're using a fourth degree Taylor polynomial, that's why we see that 4 there. So again, luckily the left side is just a matter of writing it out and setting it up. There's no actual math that ever goes on over here. We're just kind of setting up that error. So what is this Lagrange error bound telling us? Well, it's telling us that the error is always going to be less than or equal to some number that we need to figure out over here. And if we use the formula to figure that out, hopefully it will be at least somewhat straightforward. So let's go ahead and set this up. We need to find the maximum for the fifth derivative. Again, we're looking at the next term over, and since we're doing a fourth degree Taylor polynomial, that would of course mean we'd be needing to look at a fifth derivative, and we want to find the max value of that from 0 to 0.1. Again, like the problem we saw above, we need to read between the lines in a manner of speaking and determine the window that we're using here. If we're writing the Taylor polynomial about x equals 0 and we're using it to approximate 0.1, then that would of course have to be the window for the x values we're looking at. After that, we need to multiply by a fraction, and that fraction will again be x minus c. And then we're looking at the next term over, so since we're doing a fourth degree Taylor polynomial, this would of course need to be a fifth power over a fifth factorial. Of course, we're using c is equal to 0. I never wrote in that extra one, but just realize that c is equal to 0. And again, we know x, that's the value we're approximating, is 0.1. Okay, so again, I know that's the big hurdle to overcome with these Lagrange error bound problems, but once we write that, now it's just a matter of figuring out these numbers. And the big thing is to figure out this part right here. What is the maximum value of our fifth derivative from 0 to 0.1? This is a calculator problem, just like the first two problems. So what we can do is, because they don't tell us if this function is increasing or decreasing, we can look at a graph. If we take cosine x and graph it from 0 to 0.1, you'll notice that our graph is decreasing in that little window. And since our graph is decreasing and we want to find the maximum of our fifth derivative, keep that in mind, we're trying to find the maximum of our fifth derivative from 0 to 0.1. Since this is a decreasing function, that happens at the left endpoint, which would be 0. So this is kind of reverse from the first example I did. We had an increasing function in the first example, so that maximum happened at, of course, the right endpoint. The maximum of our fifth derivative right here occurs at the left endpoint, which is 0. So that means we need to figure out what the fifth derivative is at 0. And luckily the fifth derivative is just cosine x, so that would just be cosine of 0. Cosine of 0 is just 1, if you recall, and if we take that and type it in a calculator, we can of course get a decimal. This particular problem, I didn't print the answer choices. I believe this was a multiple choice question, and that actually was one of the answer choices. But even if it wasn't, you're free to just leave this as the answer, and you don't always have to get a decimal. You can leave your answers exact, and that's perfectly acceptable. So hopefully these three examples kind of illustrated how to apply this weird Lagrange error-bound formula. But again, I think just like with a lot of this stuff in this chapter 9, just take some time, some practice, and maybe rewatching of these ideas explained again in these videos.